Hello class, and welcome to the very first lecture for Module 5, the one-way between groups ANOVA. Now ANOVA stands for Analysis of Variance, and so we're going to shift from analyzing means and then start looking at the variances among our groups rather than the means of the groups. And we'll talk about that, why we do that here in a little bit. Also, I just want to let you know that we're almost to the end here. We only have 4 more hypothesis tests, so we're very close to wrapping up this semester. So we'll talk about the one-way between groups ANOVA today. We'll come back and we'll talk about the one-way within groups ANOVA for the next lecture. Now the ANOVA models are what we call F-tests. So similar to we had Z-test and T-test, we now have F-tests. So let's just take a moment and let's review all of our tests and when to use them, and then we'll continue on talking about the F-test. We first learned about z-scores. Now we get z-scores, we want to compare individual scores, such as for a single person or a single thing, and compare it to the overall population of scores. Now this is where we have a population mean and a standard deviation. So if we had a person, maybe Susan, and we wanted to compare Susan's salary to the population in the United States, we could do that if we had some population information, such as the average salary and the standard deviation of salary for those in the United States. And we could compare Susan to the entire population. And when we did that, we would get z-scores. We then learned about the single sample z-test, and we get z-test when we want to compare a sample to the overall population. And again, we still have to have both a population mean and a population standard deviation. So it's pretty much the same thing as z-scores, except now we're looking at a group of people. So maybe we want to look at 10 people's salary and get the average of 10 people's salary, and then compare that to the population made up of 10 people's salary at a time. And so what that allows us to do is allows us to remove individual differences when it comes to salary and compare a group to the overall population. After the z-test, we then learned about the single sample t-test, which does exactly the same thing. We're still comparing a sample to an overall population. The only difference now is that we don't have a population standard deviation, but we do have a population mean. And so we get a lot of population means from census data, and so maybe we're looking at census data. It doesn't give any standard deviation, so we have to estimate that standard deviation. But we're still comparing a sample to an overall population. We then learned about the paired sample t-test, and so we would use a paired sample t-test if we have no population information, so no means, no standard deviations, and that's okay because we can make the assumption that if there's no difference between the two populations, then that difference should be 0, and so we use that as our population mean difference to run our analysis. So now we'll take 2 samples, we'll compare them to each other, and of course we're inferring from those samples to a population. And those samples should be dependent on each other. In other words, they should be correlated or related in some way. And so maybe we measure the same participants twice, so like a pre-test, post-test. Or maybe we look at siblings, or maybe we look at twins, so they share a genetic relationship with each other. And any of those we can do a paired sample t-test. And then last week we learned about the independent sample t-test. Again, just like a paired sample t-test, we don't have any population information, but we can still make the same assumption that if there's no difference between the two populations, then if we subtract them, we should get a difference of 0. So we'll use that as our null hypothesis as the center point of our distribution. So the only difference between independent sample t-test and the paired sample t-test, at least theoretically, is that the samples are now independent of each other. So every observation is being measured once and only once, and we can't pair them or match them or measure the same observations more than one time. And that's an independent sample t-test. So that brings us to the F-tests, and so the F-tests are ANOVA models, analysis of variance. And the reason why we do F-tests is because now we have more than 2 groups. So with Z-tests and T-tests, we are limited to only comparing 2 populations at a time. And so we can't compare any more than that, but certainly in the research field, there will be times where we'll have more than 2 populations. And so what do? Well, now we need a new test, and that's going to be the F-test. So we could do, if we had more than 2 groups, we could do what we call multiple t-tests, and so we can compare 2 groups at a time. So if I had 3 groups, I could compare group 1 and group 2, then compare group 2 and group 3, and then compare group 1 and group 3, and do multiple t-tests. However, if we do that, there's a problem. And that problem is what is called alpha inflation. So if you remember that every time we do a test, we set an alpha, a type 1 error rate, the percent chance that if we reject the null hypothesis that we are wrong. And so when we do multiple tests, we inflate that alpha artificially. And so the rate at which we inflate it is the number of tests or comparisons we make times our original alpha. So if I have an alpha of 0.05 and I do 3 separate t-tests, then I inflate my alpha to 0.15, or in other words, a 15% chance for a type 1 error rate. So I go from a 5% error rate, a 5% chance of being wrong if I reject a null hypothesis, to all of a sudden to a 15% chance of being wrong if I reject a null hypothesis. One way to think about this is that an alpha of 0.05 is essentially 1 out of 20. So if I was to do 20 different statistical tests, I would expect at least one of those statistical tests to have occurred by chance if I reject a null hypothesis. Not because there's anything going on, but just because there's a 5% chance for each one of them. And if I have 20 of them, then that becomes essentially a given that one of those particular hypothesis tests is going to be incorrect. It's going to be an error, a type 1 error specifically. So if we take a look at an example, again, similar to what I just talked about, that if we had 3 groups, we'll call them X, Y, and Z, I could compare 2 of these groups at a time to get at all possible combinations. And so I could look at group X versus group Y, group X versus group Z, then group Y versus group Z, and I cover all my groups and I have a comparison for all possible comparisons. But as we mentioned before, we inflate our alpha, our type 1 error rate. So we end up with 3 comparisons, or 3 statistical tests, 3 t-tests, at an alpha of 0.05, and when we multiply 3 times 0.05, we end up with 0.15, or a 15% chance of a type 1 error. That if we reject a null hypothesis, there's a 15% chance that we're wrong with our conclusion. Now, of course, there is a simple solution to alpha inflation, and that's called the Bonferroni adjustment. So if we know that alpha is inflated by the multiplication of the number of comparisons, so C times alpha, then it would make sense that if we had our alpha rate to begin with, let's say 0.05, and we divide by the number of comparisons, then we can correct for alpha inflation. In fact, that's what the Bonferroni adjustment is. So if I know I have 3 different t-tests and I want my overall alpha to stay at 0.05, I can take 0.05, divide by 3, and then use an alpha rate of 0.017 for each of the comparisons, and that would solve my alpha inflation problem. However, there's still another catch. That catch is that each of my hypothesis tests that I would run would be what we call overly conservative. In other words, it would be harder to reject the null on any one of my t-tests or hypothesis tests. And that becomes a problem because now we're reducing the power. And so the question is, how can we keep power the same without inflating the alpha? And so the best way to do that is to do all your comparisons at one time. Instead of doing 3 separate t-tests, you do one large hypothesis test that does all comparisons simultaneously. And that's what the F-test does for us. So that brings us back to our question of why do we need another test, in particular an F-test. And so we need an F-test so that we can compare more than 2 groups and that we can do it simultaneously. At the same time, we'll be able to control the type 1 error rate, or the chance that we're wrong if we reject the null hypothesis. And so if we want our type 1 error rate to be 5%, then we can keep it at 5% rather than inflating it or rather than making overly conservative tests. So let's talk about the F distribution and its relationship to the T in the Z distribution. So we'll start off looking at the T and Z distribution, and then I'll introduce you to the F distribution. It is quite a bit different than the distributions that we've been used to for the most of this semester. So you'll remember the Z distribution is a normal distribution. It's unimodal. It's symmetrical about the mean, or at a Z of 0. In other words, it's centered at a Z statistic of 0. It also extends to infinity in both directions, both the positive direction and the negative direction, and it has a bell shape to it. You will also remember that the t-distribution looks the same as a z-distribution, that it's a normal distribution, it's symmetrical about the mean at a t of 0, and also extends for infinity in both directions. The only difference is that the t-distribution uses an estimate for the population variability or the population standard deviation. Let's now take a look at the f-distribution. You'll notice that the f-distribution is quite different, that it is not a normal distribution, it is not symmetrical, it is still unimodal, but it has some differences to it. And so our f-distribution here, you'll notice that it's a skewed distribution. It's a positively skewed distribution and will always be a positively skewed distribution. You also note that it's not centered at a statistic of 0, it's centered at an f statistic of 1. And in fact, it touches the x-axis at 0 and then extends on to infinity in the positive direction, therefore giving it the positive skew. And so it's actually quite different than the distributions we've used before, but how we use it will be very, very similar. We'll still specify a region where we will reject the null hypothesis, in other words, the critical region, but that will always be in the positive direction. So we don't have to worry about whether or not we have a one or a two-tailed test, because the f-distribution will always be essentially a one-tailed test in the positive direction. So in some ways it makes it a little bit easier. Now the reason why it is it's only in the positive direction, that it's only a positive distribution, is that we can't subtract means from each other when we have more than two groups. Instead, we have to compare the ratio of the variances. And if you remember your formula for variance, variance requires squared units. So if you square your numbers, then you'll always have positive numbers. And that's what the f-distribution is. Based on variances, it'll always be positive, because if we had any negative numbers, we would have squared them to get our variances. And so there's no reason to look in a negative direction. There won't be negative values. So know the difference between the f-distribution and the t-distribution and the z-distribution. The f-distribution is still unimodal, but it's now a skewed distribution, a positively skewed distribution that extends to positive infinity. It never touches the x-axis. It asymptotes gets closer and closer, but never touches it directly. It's also centered at 1, and it uses squared values, hence why it's only a positive distribution.